Welcome. This is Thursday, October 22nd, ESYS 50, lecture for week number 9. And I'd like to start with this by sharing the screen for Canvas. So let's go ahead there and make sure you can see all of this. And so can everybody see my Canvas screen? Good. So on the Canvas screen, what I have is, and let me make this just a little bigger so you can see this perhaps a bit more clearly. And let's go to here and don't. All right, that makes it a little more visible there. And oops, come back here. All right, so for week number 9, notice that the due dates, we have superposition A, due was Monday's date, and so we finished our analysis. Anybody who was participating in attendance received score points for that. And we also had measurements for A, so those score points are already in place. We also completed our Bobot activity on Monday, so the due date on Monday, those score points are also complete. What's due the coming Sunday are a couple of things. This one's really important. There's 5 video assignments that I need for you to all look at very carefully. And this is a sign-off sheet. So if I go to click open this guide, what it is that you're going to go see is this list. And each one of these are links that will help give you some verbalization on the concept of various aspects of capacitors. There is, if you don't have the ability to enable Flash or Flash is not already enabled on your computer, there is a button here to enable Flash on your computer, and this again applies to PCs and not Apples. There is a 0 task, and the 0 task is simply an Excel checkoff list, and the checkoff list goes to show you this. Let's see if I can get it to open up, and let me make it bigger, and then I'll share that screen with you. It's very easy to do. So let's go ahead and stop this share, and let's go to share the Excel sheet. And here's the screen. Screen 2 is actually very good. Go ahead and share the screen. So on my second screen, you can see the Excel sheet. So the Excel sheet is simply a sign-off sheet that allows you to check off the date when you had completed an exercise. So if you look at item number 1, electrostatic charge of a capacitor, you can see a link in this cell. And it matches this in Canvas, electrostatic charge of a capacitor, and there's a link. Both of these take you to the same place. So you have 5 items to link up and view, and upon the completion of the view, you just go ahead, put your dates in the Excel sheet, and when you have finished viewing each of those at least once, then you save this and upload this into Canvas. This by itself is a 50-point task. So these videos are very important. Let me play a little bit of one to give you a preview of what it is that you want to be able to view. And a couple of things regarding these videos. This is really good, electrostatic charge of a capacitor. And there may or may not be audio associated with this. Now, one other thing, some students initially may have a challenge looking at the WISC online video tasks. And there happens to be, if you look at the address bar, here's the address bar, there happens to be a padlock on the address bar. So if you can't see these for any reason, if you go to click on that padlock, you can see that, yes, we don't want to block Flash, we want to allow Flash, we want to allow pop-ups and redirects. So Flash and pop-ups, both of these should be in the allow mode in order for you to see, view, listen to any of these links that are supplementary to your lessons for online work this week. So again, if these don't play, come up to your address bar, click on the padlock, and then you would be able to see a choice between block Flash, allow Flash, block. So we want to allow, and the same thing for pop-ups and redirects. Pull down on this, you don't want to block, you want to allow. So both of these should be on allow, and you should be able to play this. Now, what this looks like is if I go and hit next, this goes to talk about some aspects of the capacitor, and this will reiterate some of the things that we'll be talking about today that I'll be sharing with you during lecture. So be sure to take care of those 5 tasks and be sure to put in your dates, send this in, and that is the completion of the 50-point task. Now, in addition to that, your online tasks are also, give the screen a moment to come back to us, Superposition Analysis B. Superposition Analysis B, you need to build this circuit at home and bring to class with you. And the build of it is very similar to what we've done before. The analysis paper is very similar to what we've done before. Some of you have already tried tackling this and have been pretty successful. Overall, by the time you finish part 1 and you finish part 2, you algebraically add those quantities into this table. Once you add those quantities into this table, what's really important that a lot of students don't remember is to watch the video and be sure to mark your polarities around this schematic. The polarities mark the directions of which way the electron currents flow. And the polarities will help you reconcile your loop equations, okay? So if you catch up on the previous superposition video that I had posted based on Monday's lecture, that will help you out a lot. I have no less than 2 other superposition videos in my YouTube collection. So if you go to Kogai on YouTube, you will find our superposition lecture of Monday on there. You will also find 2 other superposition lectures, and they will take you all the way through the process, including the loop equations. Okay? Okay. And aside from Jacqueline, has anybody else started to play with the superposition task? No? Okay. Well, good job, Jacqueline. I think based on your reported calculations and mine, we're within 0.02 of a decimal place, and that's excellent. So we're doing just fine. All right, so you have a superposition analysis to do. There is, and that's got to be completed and uploaded, because that is a homework assignment due on Sunday midnight. There is also a superposition measurement that that will help you with the circuit build, and you will bring your circuit build in on Monday to do the voltage and current measurements. But what I have in Canvas here, you can see 9-1 lab superposition build and resistor measurements. And this is worth 40 points. Show you what it is that you're going to be building. Here's the document. And this measurement handout is very similar to the previous measurement handout, except I don't have on here the values of currents and the values of voltages that you're going to measure. I've already measured them to confirm. So you happen to have a circuit build that shows how you need to build it. And as it turns out, remember we had 3 green wires that were hanging on this side of the board, 3 green jumpers. We don't need those green jumpers. The green jumpers would have been appropriate if we were using your breadboard power supply, this little power supply right here. If we were using this guy, we would have used the green jumpers. And so I didn't remove the green jumpers when we were in lab. And so what it is that you have is a cleaner build of the board. And you'll build this, you'll take a picture selfie of this. You will measure your resistors to make sure the resistors are in the correct position. You will not hopefully be building this in class because, as I've said, any circuit builds in class detract from our lab time. So it's an easy circuit to build, get it built in before you get here, and make sure the correct value resistor is in the correct position of the board. How will you know that? You've got to measure your resistors. You've got a digital multimeter, and you can do so. So you will fill in R1, R2, R3 measurements, and that's all you can fill in at home. You will be uploading the picture of this in addition to your superposition analysis B. Upload that, and that will be your 40 points. This goes to show a little later on what you're going to be prepared for when we come in on Monday. When we come in on Monday, you're going to be able to see, or you can see here, I've got cables on one side of the power supply supplying 7 volts on this side of the circuit, another cables on this side supplying 4 volts on this side of the circuit, and then we'll be able to do our current and voltage measurements. This goes to show my confirmation that I have 4 volts supplied on the left-hand side, and this goes to show that I have, interestingly, negative, did you catch that? Negative 7 volts on the right-hand side, because in the actual schematic, if you notice, and I'll make this bigger for you, notice that V1 has positive plate on top, negative on the bottom, whereas V2 has negative on top, positive on the bottom. So when you go and do your current directions, you want to be mindful how to deal with the current directions based on V2 moving electrons up as opposed to V1 moving electrons down, okay? So be mindful of that. So it turns out in the verification, when we come in on Monday, you go to verify these voltages, it turns out, yes, I will be presenting negative 7 volts to this side of the circuit, all right? And what that circuit looks like, and you can magnify that circuit build when you have it on your computer screen, you can look at it in greater detail. Let me move this over here and move the scroll bar over here and make this bigger. So everybody can see that. You can see this more clearly, yeah, when you magnify it, all right? So just make sure you have the right resistor in the right place. There's only 3 resistors and only 5 jumper wires on the board itself. And then I've got a jumper here for the positive 4 volts. This is ground. And then I have my black jumper here going to supply my negative 7 volts here. And my common is here, okay? So these connections with your alligators we'll deal with on Monday, but you got to have this part built. Any questions about what you're going to be submitting over the weekend for the Superposition B? Let me go ahead and close this guy out, and let's go back to Canvas and modules. All right, then we also have a capacitor worksheet, and the capacitor worksheet looks like this. And I'll give you the formulas for this in this afternoon's discussion. The formulas are a little different than resistors, but your task is to do the calculations for series capacitors. These are capacitors in series, and then capacitors in parallel. And each one of these calculations is worth 5 points. So 5, 10, 15, 20, 25 points there. And the last 2 are worth 10 points and 15 points because these have series and parallel components. So we'll see how you do on this. We will practice this in today's lecture in preparation for you to be successful with this particular worksheet. So be sure that that guy is uploaded by Sunday midnight. Not a hard task to do if you look at things carefully, and look at this very carefully. Just want to point this out to you so you can see this now and make this nice and big. Okay, is that pretty big for you on your screens now? You're asked to calculate C total, capacitance total for this first circuit. Notice the units though. They are 46 micro F. F is pronounced farad, F-A-R-A-D. Everybody say farad. Farad, okay? So this is 46 microfarad. How do you key micro into your calculator? You key micro as a 10 exponent negative 6, yes? Okay. So this is in microfarads. This is in microfarads. That's in farads. Oh dear. Something interesting there. Okay, so be mindful of that. Actually, I need to fix that. That should be in microfarads. I will fix that. Everybody make a note for C1 that this is in microfarads. Number 2, these are in P. What is P? P is the symbol for what unit value in power of 10? That's called, what, 10 negative 12, and it's called picofarad, yes? Picofarad. So all of these are in picofarads, so that one's correct. This one here has a mix. This one has microfarads and then a nanofarad. Nano is what power of 10? 10 negative 9, okay? So you want to be sure that calculates properly. These are all in microfarads. These are all in picofarads. And then this one here shows these are all in picofarads and these are all in microfarads. So I will go ahead and make one adjustment and change this one so that it's 98 microfarads instead of 98 farads, okay? And I'll change that right after our discussion. So any questions that we have this in front of us to turn in. This is a 50-point exercise. And as long as you follow my formulas and you practice with us this afternoon, you should have, hopefully, no problems with these calculations. If you do, contact me through Discord. And generally, I have Discord in the background on the screen while I'm doing other classwork. And if I happen to notice a little blip, a little alarm, somebody has a question, if I'm looking at the screen at that moment, I might even be able to answer your question pretty quickly. Otherwise, generally, I hope not to have more than 24 business hours before I answer. And if it ever goes longer than that, I apologize. Life does get in the way sometimes. So let me close this guy out. And now there's one more task to do, and that is a discussion board. We haven't done one in a little while. And so your discussion board for week number 9 is to be held in Discord. And that's worth 15 points. It's not going to make or break the grade, but it's interesting in that it's asking you to put a post, and on your post, discuss what you feel your confidence level is with respect to making digital multimeter measurements, good old digital multimeter measurements of resistance and voltages and currents on your breadboards, okay? How confident do you feel? And you want to reiterate your understanding of where the leads go. So you have leads that have to be connected, and you have to understand, just go ahead and reiterate how the probes get connected, what probe goes where, how you set this to measure resistance, how you go to set these meters to measure voltage, and how you go connect the probes. Are the probes connected in series or are the probes connected in parallel? How do you set up your meter to measure current? What settings do you use? And how do you have to change the position on our bench digital multimeters? And with these guys you do, on your red ones you don't. But if you happen to be using these, you better make note that yes, you have to change the red probe's position. And what do you have to do to measure current? You have to break open the circuit. You have to decide, well, first we have to decide where to measure current. Then at that location, break the circuit open, then make sure that this is placed in the ammeter mode. The red is positioned in the milliamp, microamp position. Then you go to place these two probes in the current path. So those are the points that you want to reiterate in your discussion post. And then your reply to your classmates, is a confirmation, a correction if they happen to have made a misstatement, and compliment your classmates for their level of understanding. That's a 15-point exercise. I'll see that in Discord, and as I see different things pop up in Discord, you'll earn your 15 points there. So, my friends, week 9 has these elements that have already been done, as we were here on Monday, and then some things yet to do by Sunday midnight, and then the actual measurements of voltages and currents for Superposition B we will do on Monday, and that's a separate lab. That'll be worth 50 points for that measurement exercise. Actually 75 points on it for that measurement exercise. So any questions in Canvas regarding what's up in front of you before we jump into our lecture? I'll take that as a no. All right, then let's go ahead and talk about today's discussion. So for today's discussion, let me stop this share and let me go to here, IPv4. This, oops, knocked my camera over, I don't know, sorry. Okay, so this goes to show where my positive 4 volts will be connected. Positive 4 volts will be connected to this red rail and introduced to this side of the circuit on R1. The -7 volts on this side for this resistor will be introduced through this set of jumpers to this red rail through this white jumper here. So I will apply my -7 volts to here. The black jumper here and this remaining white jumper over here will be for the remaining leads of your multimeter. And the measurement of all of these we've done Monday, so this past Monday. So hopefully this coming Monday, we won't take very much time at all in being able to complete this task. Yay? All right. Now let's talk about capacitors. Capacitors are a wonderful thing. Let me take this off of the camera. Let's go to here for a moment, and let's capacitors, unit 20. This will give you, in addition to the 5 videos that are posted, this will give you the additional in-depth discussion of what you need to know about capacitors. And I just moved things unnecessarily. Oops. AC circuits. Oops. There we are. All right. So this will go show what's happening with capacitors. And fundamentally, capacitors, and I'll show you the actual devices themselves. They come in different shapes and sizes. Let me actually stop this share and actually go back to camera and show you physically what we're talking about. In your kit, you happen to have capacitors. So in your kit, there and there happen to be capacitors. And do this right down here. So your capacitors come in a couple of flavors in your kit. And here we go. These little disc things. This is a capacitor, one right there. And there's several. They come in different rated values. One right there. One right there. And then you also happen to have these. They look like tiny soda cans is what they look like. And focus is a good thing. And they look like little tiny soda cans. So you have fundamentally, from a construction standpoint, 2 basic configurations of capacitors you're going to be working with. Oops, just knocked that one off the table. Non-polarized and polarized. So what are the 2 basic configurations? Non-polarized and polarized. So what does non-polarized mean? Non-polarized means they can be hooked up to your circuit just like your resistor. Do your resistors have polarity? They do not by themselves. It doesn't matter whether you take your resistor and you hook it up. It doesn't matter whether you take your resistor and pretend this is a resistor with a cap. It doesn't matter whether you hook your resistor in the circuit this way or you flip it 180 degrees around and hook it up this way. That's non-polarized. Your resistors are non-polarized. Well, we have capacitors that are also non-polarized, and you have them in your, you happen to have them in your kit. We also have polarized capacitors, and polarized capacitors, you do have to be mindful of how you connect these to your circuit board. And the polarized capacitors are marked, typically going to be marked with some kind of a marking indicating which lead is negative, which lead is positive. If we take a look at this particular guy here, you see that there is a white band with a negative symbol on here. This indicates that this is the negative lead. So let me go ahead and change this to the speaker view so we can see this enlarged. And everybody see in the larger view this white band on this side of the body of the capacitor and the little negative symbol printed on here. It goes to tell us, if I roll this over gently, it goes to show us that this lead here is the negative lead, whereas that lead is the longer lead, is the positive lead. It follows the same rationale as your LEDs. When you had LEDs hooked up to your circuit board before, what was the identifying factor that told you which lead of the LED was positive, which lead of the LED was hooked up to negative? Was the length of their leads, right? Remember that, this thing will not stop rolling around. Okay. Remember when we said that for LEDs, The lead that is longer is positive, and the lead that is shorter is negative. So it's positive to be long, negative to be short. And the same thing here, positive to be long, negative to be short. So the capacitor follows the same rationale. If it is polarized, before anybody alters these by cutting these down, as they come from the factory, if they're polarized, the shorter lead is intended to be on the negative side of the circuit. And that's why this lead over here is closest to, and if I can spin this guy around a little bit, that white stripe band on the body of the capacitor. Now these guys are relatively small. You can see by the scale of the LED that these are pretty tiny. Now capacitors do come in different sizes and also different shapes. The colors will vary as well. And so we also have other capacitors. So we happen to have these I grabbed from our storeroom. Here's another one from our storeroom. Here's, flip this over to see the value. Here's another one from our storeroom. Here's another one from our storeroom. And I will go ahead and arrange the capacitors. Put my LED back. I will go to arrange the capacitors in the two basic families of polarized versus non-polarized. So these guys here with the little crimp, cylindrical, metallic foil type cover with a little crimp on one end, these are typically going to be polarized. They look like little tiny soda cans, yeah? It looks like a little tiny soda can. And that's polarized. I put that over there. Here's another one that's polarized, and these guys here are the non-polarized ones, all right? Leads are the same length. There's no marking as to which lead is positive. Done. Non-polarized and polarized. Now, you can remember seeing that they happen to be, I'll move this further up because I've got more interesting ones to show you in just a moment. I will bring in a slightly larger capacitor. That's a monster by comparison to the other ones. This guy, is it cylindrical, and does it have this little crimp around the one side of the capacitor, and does it remind you of like a little soda can? This is polarized. And the polarized ones are the ones you really have to watch out for, because they generally can store a lot more charge. And if you look at this very carefully, I'm trying to hold this up so you can see it on the light. Can you see one of the screw terminals has a plus sign on it? Raise your hands if you can see that plus. I'm trying to get, yeah, so the glare is helping us in this case. We have to maintain proper polarity. Now, I will say this about the polarized caps. If you hook these guys backwards and you apply enough voltage, they will explode. What will happen? They will explode. And that has happened in lab. As often as I have told students over and over and over and over again, be mindful of polarities, don't hook these up backwards. And if you hook them up backwards, if a momentary backward won't hurt anything. But if you have enough voltage on this, and it is backwards, these things will explode. And even the ones in your kit, let's take a look. Let's find the big one here. The biggest one in your kit is listed as a, what the heck is it, 100 microfarad? This 100 microfarad capacitor is about will explode with about half the size of a firecracker. If you've ever remembered during 4th of July, anybody popping a firecracker, this will pop about half the size of a firecracker. You don't want to be anywhere near this when this thing explodes. It is not a good thing. Now, that's a 100 microfarad capacitor. This guy is 6,000 microfarads. This guy will be like a small stick of dynamite. And if you think that's impressive, well, I got something a little bigger for you. Here's the bigger one. And this particular guy is 13,000 microfarads. Now notice the markings here are capital MFD. They don't use the little micro symbol, capital MFD, and that is the industry standard for microfarad, okay? So 13,000 compared to 6,000. This is a much hunkier capacitor. Now, if you think that's impressive, I have something that's 200, let's rate it at 50 volts. Enter a bigger boy. Okay, This is bigger than your soda can in terms of diameter. And I'm going to show you how dangerous this guy is in just a moment. What we're going to do, if you can see on both of these capacitors, can you see the little plus symbol here? Right there's a little plus symbol. And right here, if I hold this up to the light just right, can you see the terminal that's marked plus? Okay, what I'm going to do is I'm going to charge this capacitor up to, I won't be able to charge it up to 200 volts, but I will be able to charge it up to 600 volts. Capacitors not only hold charge, they can store that charge for a really long amount of time. So that means when you, as a technician, come across capacitors in a lab, in a work situation, at a factory, you don't know when it was previously charged. You don't know how much charge there is on there. So since you don't know, are you going to arbitrarily touch these two terminals with your fingers? Absolutely not, because the spark is going to be harmful to you. So if you look at the terminals here, these screw terminals are perfect, not damaged mechanically or electronically. If you take a look at these are screw-on terminals. So we put bolts into these because they have so much current. These are also undamaged. Oh, this one's physically got some scratching. If you take a look at this one here, this one shows some physical damage for sure. Let me go ahead and focus on that. Yep, it's got some physical damage. And the physical damage is because I've sparked this and arced this a number of times. So what I'm going to do is I'm going to charge this guy up. And after I charge this guy up, I'm going to lay the screwdriver down on here and touch these two terminals together. No. Like that. And it will give you a 4th of July sparkle. It will be a loud pop, and there will be so much charge that this guy can discharge. I will damage the metal on the shaft of the screwdriver. Right now, the screwdriver is nice and clean, yeah? No damage on it whatsoever. Well, we will sacrifice this screwdriver for you because I love you guys that much. So let me show you how I'm going to do this. Behind me is one of your benchtop power supplies. Behind me is a pair of electrical leads. So it won't take me but just a few seconds to attach the leads, charge this capacitor up, and then I'll bring it back over in front of the camera. Hopefully I don't damage my camera. I hadn't thought about that. We'll see. But let's go ahead and see how we do with respect to charging this guy up. So here, let's flip it around this way. Everybody can see the benchtop equipment on the other side over there. Focus. There we go. All right, here comes the capacitor. And I will hook up negative to negative right here. I will hook up positive to positive right here. And make sure these are in a series mode. Turn down the current, turn down the voltage, turn this puppy on, double check my polarities, positive, negative, positive, negative. I don't want to blow it up while I'm demonstrating. That really would not be cool. Turn up my current, turn up my current. And now turn up the voltage, turn up the voltage, turn up the voltage, turn up the voltage. I got 30 and 30. I've got 60 volts on this right now. It doesn't need any more time to charge than this. Turn this guy off. This guy is fully charged. Disconnect, disconnect. So it charges up pretty quick. Now to protect my camera, I'll do this at a little bit of a distance, and hopefully you can see this. Let me bring this a little down like so, and then hold this here like so, and that way there's nothing in the background except floor for you to see. Clean shaft of the screwdriver, and I'm going to touch. Watch carefully. Are you guys ready? Wave your hand if you're ready.
Ready.
Here we go. Did you see that? And not only did it spark, my friends, it's completely discharged now. But look at the blade of the screwdriver. Now it's focusing on my shirt. Do it this way, yeah. That was nice and clean. The screwdriver did look like this on the other side. And now you can see some serious scorch marks. And not only are there scorch marks, but there's actually pitting of the metal where the metal has been burned away. So how much electricity do you think it would take to actually burn away metal on a screwdriver? So does that give you the impression that capacitors are nothing to be trifled with? Okay, please handle capacitors with utmost respect so that you nor anybody else near you will be injured. Okay, so are we okay with the practical demonstration of safety with the capacitor? All right, there is a method by which technicians can safely discharge electricity from a capacitor. And that method is done with one of these guys. Let me put this out here. And I'll hold this out here so you can see the whole thing. This is, it looks like a cattle prod. That's what it looks like. And what this guy is it's used for discharging a capacitor. So the metal tip is what's used to touch one side of the capacitor. And on the other side of the capacitor, we would have this cable touching the negative side. And this device will not allow your capacitor to provide the spark. This allows it to discharge safely. You'll notice that this has a hilt to protect the hand from any kind of sparking that might occur. And so the reason why this will allow the capacitor to discharge safely is because built inside the handle of this and built inside the shaft is a large value resistor. And that resistor will allow that capacitor to slowly bleed off its charge. So it won't allow it to just spark. And so technicians on a workbench will not use the screwdriver. They will use this particular tool to safely discharge the capacitor. Once the capacitor has been discharged, they will put it on one side of the workbench, and then you can safely touch the terminals without fear of spark. So this is the device that's used for safely discharging your capacitors. Everybody okay with that? Learn something new every day. Okay, cool. Next. All right, now let's talk about deciphering the values of a capacitor. And that becomes significant when you look at the markings on these capacitors. They're marked with some values. This shows a 472. A 472, we're going to decipher that. And I'll show you how to decipher that. Generally, if the capacitor is physically large enough, you would be able to see the value of the marking on the body of the capacitor. Let's see if I can focus. Oh, wow, this is pretty good. Not bad for a 4K camera. 100 microfarads, yes? And this one doesn't show you microfarads because physically this guy's really small. So all the best that it can show you is 3 digits. We have some other ones in your kit. Let's see what other ones we happen to have in your kit. We happen to have these guys. We happen to have this guy here. This guy is flip it over to the other side maybe. Can everybody see the value of this particular guy? 10 UF for 10 microfarads, yes? So the first one we had demonstrated this was a 100 microfarad. Right, there's a 100 microfarad. This one's a 10 microfarad. This guy here from a different manufacturer, the marking happens to be right where the crimp ring is, but that's also 100 microfarads. So on the larger body capacitors, there's enough space for them to print a value that is easy for you to read. And certainly on these very large ones, like these very large ones, that's 6,000, that's 6,000 microfarads. as marked there. Now, on the very small ones, and you will be working with various size capacitors, they give you a number code. I'm going to show you how to decipher that number code, okay? So here is this part of our lecture. Let me put these capacitors back in here and put these capacitors back in here and these guys here. I'm going to set aside and we're going to do this. And raise this up. So that, good. And let me get a focus. Nice. All right. Capacitor value deciphering. So on this capacitor, we happen to have a body with 2 wires, no polarity, and it's marked 472 in this case. Given that first digit equals first digit, second digit equals second digit, third digit equals number of zeros, and then followed by PF. Okay, number of zeros, comma, PF. And I'll show you what I mean. So if I'm showing a 472, first digit's a 4, and that represents what? My first digit, so I'm going to write down 4. So this guy will decipher to be 4. And then you have my second digit represents what? My second digit, which happens to be a 7. So my second digit is a 7. So far, so good. My third digit represents what? Number of zeros followed by this thing PF. So 2 tells me how many zeros am I going to write here? 2 zeros. Here's a 0, here's a 0, and then P capital F. Lowercase p for pico, F for farad. So we would read this as picofarads. Okay. That's the value for this particular capacitor. Now, is this proper engineering notation? No. Why is this not proper engineering notation? We have 4 digits here. So if you go to key this into your calculator, and we'll go ahead and do that. Here's your marvelous little $8 calculator. It's $8.98 now. Aren't you glad you bought it when it was less expensive? All right, so it is a 4700. And how do we key in pico? Pico would be our exponent, change sign. Remember to change sign because it's a negative power of 10, and pico is negative 12. So do I have 4,700 with the 10 negative 12 signifying my picofarads, and I will hit equals. When I hit equals, if this goes into scientific mode, I can get it into engineering just simply by hitting the engineering key. Let's see what happens. It happened to give us an engineering mode. How do I know? Because my power of 10 is a multiple of 3, yeah? So what is this? This is 4.7, 10 power negative 9. What is this? Would this be, would this be normally be interpreted? Yeah, would this normally be interpreted as 4.7 nanofarads? Okay. Yeah, in proper engineering notation, this would be interpreted as 4.7 nanofarads. But I will say this: there are exceptions to proper engineering notation. And what are those exceptions? Caps are one of those exceptions. Throughout the world, caps are standardized to not use all the different engineering notation prefixes. There's only a few that are used for capacitors. They are as follows. They are shown as farads. They are shown as microfarads. And they are shown as picofarads. So you happen to have 10 power of 0. You have 10 power of negative 6, 10 power of negative 12. That's all you have for capacitors that we're going to be playing with. There are no 10 power negative 3s, 10 power negative 9s. So in other words, there's no millifarads and there's no nanofarads. Those units are non-standard in the world of capacitors. So even though we have been trained since the first day we've been together to use proper engineering notation, capacitors do represent an exception. And that exception is we're going to stay with farads, microfarads, or picofarads. So given this particular interpretation of this being 4,700 picofarads, we're not going to convert this to 4.7 nanofarads to maintain proper engineering notation, okay? We're going to stay with, in this case, pico. Why wouldn't we change this to microfarads? Because in microfarads, this guy would be 4,700,000 microfarads, and that becomes way too cumbersome. So even though microfarads is a standard capacitor value, 4,700,000 microfarads is just way too high, okay? So we're going to do it this way. And let's see, did I interpret that properly? Maybe I didn't. This would be nano, and then, whoops, it goes the other way. If I went to nano, it's 4.7. Sorry, it went the other way. Had a brain fart. And go the other way. 1, 2, 3. Okay, so this would have been 0.0047 microfarads. There we go. Too many decimal values in front of micro. So 4,700 picofarads would be the way that we would interpret this. So understand, no millifarads, no nanofarads. You get to do one. You get to do one. Oh, by the way, we said that this is 4,700 picofarads. Guess what I have to demonstrate? Look at this tool. I didn't say toy, I said tool. All right, this is not a toy, this is a tool. Some people think of it as a toy. All right, this will measure capacitance. So I happen to have 2 leads, I happen to have on-off button and a test. So I'm gonna hook this guy up. And sometimes capacitors are notorious for being marked something, and they actually measure out to something else. This one, I believe, is a good capacitor. Looks like a quality manufacturer. And let's see if this guy works out anything close to 4,700 picofarads, and whether this conforms to the capacitor standards of value test. Monitoring for a component, or it might be too low. Yeah, it's too small. Darn, can't test this particular one. However, I did grab a couple of other ones just to show you that the meter does work. Here is another capacitor, and let's go ahead and measure this bad boy. Nope. And this one has one. Oh, look at that. It is 16.22 microfarads, 16.22 microfarads. And it's coded as a 156, is that right? Oh boy, the tolerance on this guy is pretty far off. But 156. Let's see how we would decipher a 156. Okay, move my toy tool over here, sorry, tool. Okay, 156. Let's say number 156. Go. Don't wait on me. What's my first digit? 1. What's my second digit? 5. What does this 6 tell us what we need to do? Number of zeros. How many zeros am I writing? 1, 2, 3, 4, 5, 6 zeros. Followed by what? I have to follow this with something. What was the standard? PF, okay, picofarads, yes? Okay, let's go ahead and key this guy in. Let's see if I do a quick change. If I move over 3 here, then this guy would be here nanofarads. If I move over another 3 here, this would be microfarads. So this would be approximately 15 microfarads. just by moving my decimal point every 3 places to get to nanofarad to get to microfarad. If I could do this on the calculator, you can also do this on your calculator. Key in 1,5 and enter your 1, 2, 3, 4, 5, 6 zeros. And then remember, exponent -12. Yes, there's mine. And they hit equals. And it's non-engineering. So what do I need to do? I hit engineering. And what do I have? 15 microfarads. So did my calculator give us 15, and did my moving of the decimal point every 3 places also give us 15 microfarads? So do we have reasonable confidence that we have decoded this particular capacitor that was marked as a 156? Let me just unclip this for a moment so you can see this a little more clearly. It's marked, not Josh and you, 156, yes? So this looks like it should be a 15 microfarad cap. Let's come up here and bring in our tool, this guy here, and focus. And now let's go ahead and measure this fellow and see if we come close to the 15 microfarads, or how close we come. This looks like it should be a quality capacitor. It shouldn't be too far off. Let's see what happens as a result. This guy's here. Turn this guy on. Whoa, okay, so we do have some margin of error, don't we? Clearly we do. We interpreted 15 microfarads and it shows us 16.20 microfarads. Is our scale correct? In other words, is our engineering prefix correct? Definitely. Microfarads there, microfarads there. The numerals, however, we calculated 15, 16.2. We're going to expect to see a lot of this kind of discrepancy in capacitor values. It's just going to happen. It's the nature of non-polarized capacitors in many, many instances. You have to pay a lot more for very accurate capacitors. This one here was coded, the body of this guy is coded at 100 microfarads. Go ahead and hook this guy up on this lead. Come on, alligator, here we go. And go to hook up this lead over here. So it's coded 100. I know this one didn't measure 100 because I did this earlier. Yeah, it's still microfarad, so it shows us the appropriate scale for what this interprets to be, but instead of 100 microfarads, what's this come out to? 86.40. That's quite a ways off. Now, some are not going to be that far off. The ones in your kits, these guys here, go ahead and pull this big bad boy out. That one, pull out one of those and pull out one of those. Okay. This is marked as a 10 microfarad, and this is, let's see what this measuring C. That's not bad. 9.78 microfarads for a 10 microfarad capacitor. We're getting within the same range of tolerance as your resistors, eh? Because your resistors were never spot on. Now, let's go ahead and check this particular guy. This is a 100 microfarad cap, and clip and let go. Yeah, this one's pretty far off. It's supposed to be 180, just like this. So we're not going to rely on these 100 microfarads very, very much for our experiments. What we ought to do is when we get into AC circuits and the value of the capacitor is critical, we want to use a capacitance meter to double check the cap value so that we can make sure that our quantities are correct. This is supposed to be, what, 6,000 microfarads? Now, I'm not sure if this is too large for this meter, but let's see. I've not done one this size. I think I'm just going to have to touch these. Okay, touch and hold. Oh, leaky. How about the other way? Okay, it's supposed to be 6,000. Where are we? 7,329. Boy, I'm glad we measured this before we put this into a circuit. So before we go to utilize capacitors in any electrical circuit, you want to make sure we measure them so we will find either a physical capacitor that is closer to your ideal result or use the measured value, okay? Okay, that's this guy. What are these? This was 19,000. Let's go ahead and check this guy just for giggles and laughs. 19,000, how close do we come? Give it a moment. Oh, okay, not that bad. It's not great, but not that bad. 19,000, I get 17,450. That's okay. And then for my 10,000, this was the big one. Hopefully I haven't damaged this too much after discharging it so many times. Let's go ahead and check this guy. Oops, come on, am I touching? There we go. Touch and hold, measuring. Oh, for 10,000, I'm at 9,412. I can live with that. That's okay. That's like 5%, less than 5, about 5%, which is the tolerance of many of the resistors we've been using. Cool. All right, so now you've been introduced to capacitors that are non-polarized and then capacitors that are polarized in all different kinds of shapes and sizes, and that you've been introduced to a capacitance meter. Now let's talk a little bit more about what goes into a capacitor and how we're going to be able to calculate these guys to be in series or in parallel, because the formula is pretty easy. I will go and take us back to our textbook. Everybody see my textbook okay? All right, now fundamentally, they'll show you the capacitor symbol as being two parallel lines, or possibly a single line that is perpendicular to your wires and a second line that is curved, like this particular one here. This is a polarized capacitor. The ones that are shown with a pair of parallel lines are non-polarized. But if it's shown this way with a curve on one plate, we call these plates, and a straight line on the other plate, this tells you it's polarized. How do you know which side is negative? How do you know which side is positive? This isn't marked, but I'll tell you now that the straight plate is positive and the curved plate is negative. Which plate is positive? The straight plate is positive and the curved plate is negative. Now, physically, what is the construction of a capacitor? Physically, the construction of a capacitor is said to have a conductive plate on one side attached to a lead, another conductive plate on the other side attached to a wire, and in between is a very special insulator called a dielectric. Everybody say dielectric, dielectric. And it is a special type of insulator. I'll get into more detail of this. So you have two plates that are separated by some kind of an insulator. So what happens here is if I attach a capacitor to a battery, what will happen is the electrons will come over and accumulate on one plate of the capacitor. The electrons that were normally on the other plate are going to be moved off of that plate and go towards the positive side of the source. So in other words, for every electron that comes over to the bottom of this illustration, one electron goes over back to the positive. So what you see here is an accumulation of electrons on one side and a depletion of electrons on the other side. So when you have two sides that are conductive, one side has more electrons and one side has less, is there a difference of charge between the top plate and the bottom plate? Big difference. How much of a difference? A big enough difference that could spark and injure us. So the job of the capacitor, fundamental job of a capacitor, is to store charge and release charge. Store charge and release charge. Okay? We'll see how this is beneficial to us when we put capacitors in circuits. But fundamentally, what do capacitors do? They store charge and they release charge. Does that sound kind of like a battery? Doesn't a battery store charge and doesn't it release charge? It does. Capacitors are not a battery. Can you use a capacitor like a battery? In some instances, yes. But a battery is constructed of different materials and is more reliable to be used as a battery. Capacitors, on the other hand, are made of different other different materials, and they have characteristics that allow very quick discharge, like that spark, and then in other circuits that charge and how fast it charges or discharges can be helpful to us. So here we go. A battery is on this side. We are charging this capacitor. We have an accumulation of electrons and very few electrons on the top. If I go to hook up a voltmeter here across the capacitor, guess what? My voltmeter will measure the exact same value as the battery. So if I start off with a 5-volt battery or 6-volt battery, the capacitor will charge up to 6 volts. If I start with a 10-volt battery, this capacitor will charge to 10 volts. What do I have to be careful of? I cannot exceed the rating of the capacitor. What happens if I exceed the rating of the capacitor? It could be damaged. It won't explode, but it can be damaged. It will explode if I exceed the rating and I hook it up backwards. Then it will explode, all right? So capacitors will store whatever the capacitor charges up to. So if this is a 12-volt battery and this is charged to a full 12 volts, then I will be able to measure 12 volts on that capacitor. Now, once I remove the voltage source, I will still be able to measure that voltage on the capacitor, because a voltmeter will not discharge the capacitor. The voltmeter has an insane amount of ohms. So it will not discharge a cap. If I leave this on long enough, like overnight, it will probably discharge the capacitor. But if I do a momentary connection to measure this, it will be the full value of whatever the capacitor charged up to be. Now, next illustration, this goes to show some migration of electrons through the dielectric. This is not a good thing because the dielectric is supposed to be an insulator, and the job of an insulator is to block electricity. Well, if I have any kind of migration of electrons from here where they're abundant to this side where they're deficient, then that's called a what? Leaky capacitor. And leaky capacitors are a big problem in many kinds of electronics. How many of you have seen either a flat panel TV or a flat panel computer monitor all of a sudden have black lines horizontally going through the display? That is a sign of a leaky capacitor. Okay, when you see black lines that go horizontal black lines through a display of a flat panel, very often that is the sign of a leaky capacitor. So when they leak, they can wreak havoc on other kinds of electronic components they're hooked up to. The book goes to talk about other things that are very interesting, dielectric stress and other things. It's wonderful. Here's some more interesting things. Now, this is very important. This goes to show materials that are often used as insulators. So these are all insulator materials. All of these are different kinds of insulators. Air is an insulator, okay? Ceramic, which is a clay, is an insulator. Even paper is a good insulator. Normally, you would think of rubber. Rubber is a good insulator. And there are oils, insulating oils, that PG&E uses. PG&E uses some carcinogenic, unfortunately, carcinogenic oils in the transformers on telephone poles, and that's another discussion. But there are insulating oils that don't conduct electricity that are used in capacitors. Mica, paraffin, porcelain, even pure water. Pure water, interestingly, does not conduct electricity. Did you know that? Pure water is non-conductive. You cannot be electrocuted in pure water. If, however, you're standing in a puddle in a street, which is not pure water, it's got some minerals in it, you can be electrocuted if a power line falls onto that puddle. All right, but pure water, you're safe. Glass is a good insulator, rubber is a good insulator, Teflon. So there's a number of materials. Each of these materials has a different, look at these words, dielectric constant. We won't get into the calculation of the dielectric constant, but what I want you to impress upon you is this. A lot of the capacitors physically are named after the kind of material that's used in the capacitor as the insulator material. So when we refer to ceramic capacitors, those little brown things in your kit, those little brown capacitors in your kit, Those are ceramics. So if you look at my little photo inset, these are your capacitors, the little brown things in there are ceramic capacitors. We also have other type. We have the mica, mylar, we have different kinds of plastics. This yellow one that I had earlier, this is a plastic derivative. Exactly which one, I'd have to look up the spec number, but it could be mylar, it could be tantalum, it's one of the plastics. And next, constant, we won't talk about. Okay, this we won't have you do the calculation of, that's nice. All right, now, we have capacitors in parallel and capacitors in series. So let me give you the formulas for capacitance. And they're really easy. Cap formulas. In series. Series means like that. C1, C2, C3. If these were resistors, how would we calculate a R total if they were resistors in series? The math would be what? Sum. In capacitors, they work exactly opposite formula of resistors. My CT in series is a reciprocal formula. 1 over C1 plus 1 over C2 plus 1 over C3. So if you were presented with this, if this guy was a 10 microfarad and this guy is a 30 microfarad and this guy is a 75 microfarad, if these were your values, you do not sum these. These would not be 40 plus 75, 115 microfarads. No, no, no. You don't sum these in series. You use the reciprocal formula. And how do I calculate this using the reciprocal formula? Is going to be 10 EXP, and micro is what? Negative, so you have to remember the change sign. And micro is what power of 10? Negative 6. So have we keyed in 10 micro? And using the reciprocal formula, you're going to need to use your reciprocal key. X negative 1 is your reciprocal key. Then you're going to use a plus. Then it will be 30, and then EXP, change sign, 6, reciprocate that, then plus. Now we have one more capacitor, will be 75, EXP, negative 6, and then we reciprocate this. Do I hit plus one more time? No, I do an equal sign, and then followed by my reciprocal key one more time, followed by my equal sign one final time. So if I use this keystroke sequence, I will have entered 10 micro reciprocal plus 30 micro reciprocal plus 75 micro reciprocal equals reciprocal equals. And if you use a reciprocal formula on these values, you better end up with a value that is what? Smaller than the lowest value. Reciprocal will always end up with a total that is what? Smaller than the lowest value. So I better end up with something less than 10 microfarads, yes? Let's go ahead and do this on my calculator, your calculator, our calculator. And I will go ahead, 10 exponent change sign 6, and hit my reciprocal key there, and hit plus. That's my first line. Then I have a 30 exponent negative 6, hit reciprocal, hit plus. That's my second line. Now I'm going to do 75 exponent negative 6, reciprocal, then equals. That's my third line. Then I have to hit reciprocal and equals one more time. And I do land on a power of 10 that is a multiple of 3, so this is micro. And how many micro do I end up with? Hopefully 6.82 microfarads. Is that correct? Is that what you all end up with? Okay. So the calculation, you've done reciprocal calculation before. You just have to remember, interestingly, for capacitors in series, you got to use reciprocal. And by the same token, if I have caps in parallel, so caps in parallel would look like this. Here's a cap, and here's another cap. And I'll do one more over here. There. So I have a C1, C2, C3. And I'm going to make these guys, oh, I don't know, 33 picofarads, 17 picofarads, 80 or 811 picofarads. So CT in parallel is going to be the sum, C1 plus C2 plus C3. We're going to do the sum. So it behaves in series and parallel opposite of what you've done for resistors. So if we go to sum these, that's 50, 50 plus this would be 861 picofarads. That's using mama's calculator between your ears, right? Okay, so this would work out to be 861 picofarads, that quantity there. So are we okay with the formula for caps in series using reciprocal formula? So caps in series, the CT equals always less than smallest C, smallest cap, okay? Anytime we're playing with caps in series, if I use reciprocal formula, my total will always be less than the smallest cap. My smallest cap was 10 microfarads. In this sequence, my CT calculated to be less than 10 microfarads. If we go to play with caps that are in parallel, well, we use the sum method, and that's just straight sum. Now, we'll show you something that'll help prepare you for the more interesting circuits, and that is caps in series dash parallel. Caps in series parallel, and you might see something like this. One, silly me. Started drawing resistors. Caps in series dash parallel. So you might see something like this. Here's a cap. 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 And I'll just hold this here. So we have a C1, we have a C2, C3, C4, C5. And the way you work these guys out is the same way that we work out our resistors. If I'm looking for CT over here, I'm going to start looking at these on the wire that's attached from here, looking back towards my measuring point. If I'm looking on this wire, what relationship do I see between capacitors? C4 and C5 are what relationship?
Parallel.
Series.
C4 and C5.
Series.
They are on the same wire. Whatever currents here can flow through here. So 4 and 5 are in series. Okay? So what I happen to have here is if I do a redraw, there, my C3 is here, my C1 is here, my C2 is here, and over here, these guys become CEQ1, which is equal to C4 series C5, yes? How do I handle capacitors in series? And let me give you some quick numbers. Let's say all equals 100 microfarads. That'll just keep things simple for us, okay? All of these are 100 microfarads. So if this guy is equal to 100 microfarads and this guy is equal to 100 microfarads, and they're in series, what did we use to calculate capacitors that were in series? Didn't we use reciprocal formula for series capacitors? So we would do these two guys using reciprocal formula. So that would work out to be 100 exponent negative 6 reciprocal plus another 100 exponent negative 6 reciprocal equals, and then reciprocal, and then equals, yes? Isn't that reciprocal formula applied to a series relationship? This is in series. And so if you do this correctly, you should end up with 50 microfarads, yes?
Yes.
Because you can use a reciprocal shortcut on this. 50 is half of 100. So this, my CEQ number 1 is equal to 50 microfarads, yes? So now we've taken 1, 2, 3, 4, 5 caps and now reduced it down to 4. As I'm looking, I'm still looking for CT over here. So as I'm looking at this, again, put my eyeball here, farthest away from my measuring point. What do I see on this wire? I see a C equivalent, and what's its relationship with C3? These two are what relationship?
Parallel.
Parallel. Did I have a method of calculating caps in parallel? What do I do with caps in parallel? I am going to sum, yes? Is that right? So I can redraw this one more time. I'm running out of space, but I can redraw this one more time. Right to here. Dunk, 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 dunk. And now I have a CEQ2, which was C3 in parallel with CEQ1. Is that right? Isn't that a 100 microfarad in parallel with a 50 microfarad? Yes? Now keep in mind, my C1 hasn't changed, my C2 hasn't changed. But how do I put capacitors? How do I calculate capacitors that are in parallel? What did we do? In parallel, what did we do? We sum them, yes? So what is the sum of 100 microfarads and 50 microfarads?
150.
150 microfarads. So my final drawing on this particular guy, let's do this a little large here. My C1 is here, C2 is here. This guy is equal to 100 microfarads. This guy is equal to 100 microfarads. This CEQ number 2 worked out to be 150 microfarads. Do I have enough information now to calculate the total of these in series? Now, do I add these guys in series for capacitors? Am I supposed to add? No, because in my series right here, series caps, what do I use? My reciprocal formula. And what did the total will be? The total will always be less than the smallest cap. Well, guess what? I've got 3 in series, so my total better be less than 100 microfarads, yes? So in this particular case, what am I going to do? Reciprocal formula, so it'll be 100 EXP negative 6 reciprocal plus 150 EXP negative 6 reciprocal plus 100 EXP negative 6 reciprocal equals, hit reciprocal, and equals one more time. And so we should have 50, turn this on, that might help. Reciprocal plus 150 reciprocal, hopefully you end up with a, what, 37.5 microfarads? Is that what you all calculate? 37.5 microfarads is my C total for this circuit. So when I analyze series parallel, I will go through these steps. It helps if you do redraws along the way. It helps if you do and show your work and calculations along the way. So this is actually all of this. And if I put this in, kind of see the trail like so. It started up here and we did this, and then we ended up here. Okay. Okay. All right. This is plenty for us to do between now and Sunday. Look at the videos. There's something really important about time constants that you really need to look at. Look over that video more than once. It would be very helpful to you. Are there any questions between now and Monday as to what you need to prepare for, what your homework is? And if not, I'll put us out of the camera view. I'll take us out of the camera view. Go back to gallery view, and gallery view. Here's all of us, and somewhere here was a cell phone. Oh well, you're all on the video. So wave at us on the video, and we'll see you on Monday. Yes, and if questions come up, as they have in the past, just go ahead and post them in Discord so other classmates can see the questions, and you may be able to answer each other's questions. In fact, that's what I like to foster, is you guys helping each other out. And if I see that people are occasionally stuck, I'll chime in and throw in my 2 cents and try to help everybody out as well, okay? Okay, so with that, everybody, have a blessed weekend, and we'll see you all on Monday, all right? Take care. Adios. See ya. And go